All right, hello world. Um, it's a little loud outside. Uh, so here's the link. Sorry for the long intro. I'm usually here in like 2 minutes, but anyway, here's the website. Of course, I made a new note. I usually post a new note every like 2 weeks because there's a full set of problems at that point. I post every weekday a new problem, and you can filter it out here by the topic. But because there's like 10 topics here, that means basically every 2 weeks it cycles back around. So if you're only interested in the calculus problems, that should be all the ones ending in 3, conveniently enough. And but a new one pops up every 2 weeks. In the future, I'll probably slow this down a lot and just do like 2 problems a week. Um, but for this first set, until like November, I'm planning to do 16 questions in each topic. Um, and the 16 questions, at some point I mentioned it, well, I mentioned it again recently. The concept was to like mimic a course. So that's sort of how I'm organizing where the questions are coming from and the difficulty level, for instance. Because otherwise, it would just be like a random calculus problem. We don't know how hard it is or how to track, what topic it might be or anything like that. So, yeah, my thought was we'll pretend there's 16 weeks in the course, and I'll split however many chapters in the book that I'm using. The books I'm using are down here. These are references. I'm not using all of them. So, for instance, the real analysis book I'm using right now is Rudin, not Folland. But like maybe next year at some point, I'll probably start using a bit of Folland. Same with Conway. Like right now, I'm using a simpler, like an introduction, an undergraduate level book, Brown and Churchill, to do complex variable questions. But next year, it could be a little bit more proof based using Conway. When I say next year, I mean like this first set of problems will end in like mid-November. So at that point, we'll start over again from week 1 with all the topics. But I might be switching books. In fact, I've picked up a new linear algebra book to use for the next set, for the second set of problems. But anyway, second sequence of problems, I guess I should say. Um, so anyway, that's one thing. And also, I'm trying to stream pretty regularly, so I think on Fridays I'll be posting my answers. Even though like today's problem was only up since midnight, that's okay. What are the Fridays? 3 and 8. So it must be, yeah. Sometimes it ends on abstract algebra. So like last Friday, this was the last problem that we did, number 28. Today, the current problem is this. This will be the last problem we do. I'm going to start with 29. It's a real analysis question that says, again, this is probably like week 3 of a real analysis undergrad course. Um, these are the previous ones. So this is like a question from chapter 1. This is either chapter 1 or 2. This one actually we might be starting, because we're talking about limit points, so we're clearly getting somewhere. Might be chapter 3. This is actually a pretty straightforward one, thankfully. Sometimes I post problems based on whether I can do them. This one I know how to do, I think. Construct a bounded set of real numbers. So when we make this, you know, this example, it'll just be on the real line, evidently, with exactly 3 limit points. Well, what I'm picturing for a limit point is, what I always picture is like 0 is a limit point for a bunch of fractions. Usually I'm picturing fractions for some reason as like rational numbers as the things that approach some limit. They don't have to be They don't have to be like this example, but that's what I'm going to go with. So if I had, first of all, a set of numbers like this, natural numbers, for the denominator, I know that this set has 0 as a limit point. And I guess just to make this a little bit more rigorous, what I mean by a limit point is if you take any neighborhood, no matter how small, any neighborhood around this point, it will contain actually infinitely many. But the definition is just that it contains at least one point from this set. It'll always intersect something in this set. It's okay if it intersects other stuff too. But the point is, if you take a neighborhood containing this, it will contain, when I say neighborhood, I mean, I guess, an open set. If an open interval, say, any open interval that you can think of, if it does contain 0, it also contains some sort of rational 1 over something with that form. So I'm basically just going to take this set. This is an example of one limit point. This is like the first kind that I think of. I'm going to take that and I'm just going to like add integers to it. We could even just add 1 because it's not like this set alone with the natural numbers, it doesn't tend to any other limit points. If you took the point like 1/10, then eventually you'll get smaller and smaller. Like say you take something with radius 1/100th away from 0, it'll contain various stuff. It'll still be of this form. Well, yeah. I guess I'm misspeaking. 1/10 would not be a problem either, would it? Well, this is what I'm saying. It would have to be 1/10 plus some stuff, because eventually you're going to be less than a tenth. Like if this is 1/10, and we're only a whole tenth away from 0, my claim is that this is not a limit point. I don't know why I'm going off on this tangent about this. This is way more than the question called for. But my claim is this is not a limit point for this particular set. You would have to make a new one, like 1/10 plus this, and then it would be a limit point again. But like right now, as soon as we get bigger than 10 for this n value, well, you're no longer like in the vicinity here. At 11th, we're here. 12th is like here. 13th is like here. It's getting smaller and smaller. So if you take some neighborhood, some small neighborhood around a tenth, it doesn't always contain stuff exactly of this form. The stuff that's near it is like 1/9, 1/8, 1/11, 1/12. And if you zoom in, those are pretty far away actually from 1/10, and it's easy to construct. I could just take the distance from 1/10 to the nearest neighbors, 1/9 and 1/11. I could take the minimum of those differences and even just cut them in half or something, and I could easily construct a neighborhood that doesn't hit things of this form. But again, we can fix this. All we have to do is add 1/10 to this, and then suddenly, boom, that's a limit point again for that new sequence. Anyway, I'm really beating this to death. My plan was to just take, this limit point along with this type of sequence, and then just attach 2 more. Do this again, but for other integers. We could even just do 1 with 1 plus 1 over n, and 2 with 2 plus 1 over n. That's totally fine. That would give you 3 limit points just at 0, 1, and 2. So that's what I'm going to do for today. And then I have to be a little careful with the sequence. It's not 1 over n anymore. It's this form. So that the difference is 1 over n, and so that difference shrinks to 0 as the n's get large. And that limit concept there, where it shrinks to 0, is really what's forcing these to tend to that. It's really what's forcing there to be an infinite number of these guys. Like the tail end of this sequence is always contained in some neighborhood, and any neighborhood, I should say, of that limit point. So here's one. This thing is, I'm really just taking 0 and 1 and all the rationals that approach it from the right well, not all the rationals, but I mean all the maybe harmonic numbers that approach it from the right. And then we'll do one more. Let's do 2, say. And that should be good enough to answer this question. So 0 and 1 and even 2. And you don't have to worry about there being some sort of overlap. There is some overlap. Like this number 2 is also in both of these sets. But actually, I guess just this set. Yeah, it's in this set because it's 1 plus 1. Sorry, I guess it's not in this sequence. But, that's not important. That's not the point. It doesn't actually affect anything. It's not saying that it contains like all of these sequences. It's saying that if you take a neighborhood around a limit point, it should contain one of these, one of the set that you're saying is consisting of the, what are those called? Well, anyway, the points that are approaching the limit. This chapter would also be the one where they talk about like interior points, and maybe exterior points. Anyway, I'll move on. So that's the first one. 3 limit points. I just went 0, 1, 2. You could do like anything. You could do 1, 10, 100. This is an easy example. I'm sure there's other. Like you could do sine of 1 over 2 if you wanted something kind of a little more interesting. You could do sine of 1 over 2 approaching 0. That would be another way to make this second set of this second sequence, this infinite sequence that tends to some sort of limit. Anyway, let's move on. Second one says, this was 29. Second one says, we're given this function, a complex valued function that lives on the complex numbers. So f goes from c to c. They want us to decompose it. They want us to write it as, I forget what the specific question was in the book. Probably they did it in polar, and I decided to add it in rectangular. I don't know. Anyway, write this as the whole point here is that you can make a real and an imaginary part. So let's first do it in rectangular coordinates like this. So we just stick with x and y. So I'm thinking of z as this in rectangular coordinates in the complex plane. So x units to the right and y units up. And that's how I'm picturing a typical input from the complex plane. But what we do to our input is this. We take it, we just do the identity, we don't do anything to it, and then we add the reciprocal of it. There might be a more clever way to write this, but maybe I'll leave that alone. I don't think we're going to need it. I'm not going to use that, I guess. So basically just substitute however you're picturing the input, substitute that for z, and you'll have to do some algebra because you're trying to separate this. You're trying to write it as a chunk that doesn't depend on I at all, and then another chunk that does. So you'll factor I out of that piece. And here we should have two real functions. U and V should both not depend on I at all. That's sort of the whole point, is you want to separate it out. So you do a trick that's similar to rationalizing the denominator, if you're familiar with that. What I mean is, little review of this trick. If you had something like, well, it's more than just rationalizing the denominator. If I had like root 3 down here, you can multiply by root 3 over root 3, right? So yeah, we're doing something like that. We're actually going to go a little more complicated. So suppose you had like, I don't know, 2 plus root 3, and you still want to rationalize the denominator. What you usually do is multiply by its conjugate, 2 minus root 3. You have to do that on top and bottom so you don't actually change the number. Upstairs, you just multiply across and you get our little conjugate guy. But downstairs, the whole point is that you're going to get a difference of squares. It's going to square this term. And for us, in this example, we're not going to have a square, well, we'll have the square root of -1. That's the point. So it's exactly the same trick. Here we would get 4 minus the square of this number, because the middle terms cross out. In the middle you get 2 root 3 and -2 root 3. So here I'm getting 4 minus the square of this number. The minus sign is because there's a negative there, right? So minus root 3 times root 3. So you get a 1 here. Anyway, that's the end of rationalizing the denominator. But you would have to know that. You'd have to already be familiar with this algebra trick. Because that's what we're about to do. So our function is x plus iy. And I guess you already know part of these. So like u is going to have an x in it, and v is going to have a y in it. If that was all that was there, if it was z, we would be done. But we've also got this term. And we need to factor the I out somehow from this term. So what we're going to do is multiply and divide by the reciprocal, or sorry, the conjugate, excuse me, of this factor downstairs. So we'll put x minus iy. And then when we distribute across, we'll get x squared. And we will get minus, but it'll be minus of iy squared. Maybe I'll do this slowly. Upstairs we get this. Downstairs we get x squared minus iy squared. And when you square I, of course, you get -1. So this is I squared y squared, which is -y squared. That's the thing that you're subtracting. So you end up adding. So that's a cute thing that happens a lot. Like if you took 1 plus I times 1 minus I, it gives you 1, and then instead of a negative, it actually gives you plus, I'm expecting this to be 2, I guess. It's 1 minus I squared, but I squared is -1, so it actually adds and you get 2. Right? It's pretty handy. These complex numbers are useful things. So anyway, this downstairs has become a plus y squared, I believe. And then upstairs you got this, and you can see we can now split this up. So, oops, sorry, I forgot my plus. There's this part. I'll just put a little arrow here. So our function is actually x plus iy, and then you've got this fraction, x over x squared plus y squared. And then you've also got this fraction, y over x squared plus y squared. So if you just sort of grouped them differently, these two factors, or these two terms have I as a factor, and these two don't. So we're just about done with this easy part, with this first rectangular part. Here is part of the function. I suppose you could also write this as magnitude of z. You would usually square the real and the imaginary parts. So here we get like x squared plus y squared. So a little comment to myself, but we're not going to do that, I guess. It's not really necessary. Plus we want it in terms of x and y. I'm introducing this weird z creature now. It doesn't make a lot of sense. So anyway, so these two parts are real, and then there's two imaginary chunks, the y and the -y over blah. So we're going to add I times, there's a y, and there's a -y over the square. Like that. And that's it for the first part. This is u. This is v. And then take the same function and do it. So now I'm looking at part 2. In polar coordinates, you would write it as e to the it times some radius. So same function, but this time I'm going to think of this as r e to the I, like theta, or r e to the it. Here r is the magnitude of z, if you need that. But I'm just going to plug this in here and see if we can, like, another thing you would need to know is e to the I theta is cos theta plus I sine theta. So you need Euler's identity. But this first part then is r e to the I theta. So we can already split that like cos and sine. Those are the two, the u and the v in this case, the real and the imaginary parts. So this splits using Euler's identity, or it, I don't know, decomposes, I guess I should say. It partitions, too complicated of a word. And then there's this, which if you want it upstairs, you can just make this exponent negative. The 1 over r we're just going to leave as is. You could write that as this if you want, but it's a real number. The r is like sort of like a radius, and I guess I never drew it. So they're picturing something like that. If this is your complex number, you make an angle, and you've got a magnitude. Those are polar coordinates. So yeah, this is 1 over that radius. It would have to be positive unless the complex number was 0, right? Yeah, it would have to be positive. And then this part we're going to write like that. So really the angle just became negative theta. So this is, we're almost done with this. We're going to have 2 pieces here and 2 pieces here, and that's about it. That'll be our u and v. So for this we have r cos plus I sine like this. And then for this one we have 1 over r, and then a very similar computation. This is still plus, but the argument inside is negative. So I'm going to use some trig facts. Like first of all, this is an even function. Cosine is even, so it doesn't matter if you plug a negative in. Whereas sine is odd, you're going to get negative sine out front like that. So this one we're going to leave alone. We're just going to distribute the r and get something like that. So there's one term in each of our functions. And then over here I'm going to get plus 1 over r cos. I'm going to go ahead and get rid of that negative angle for cosine because it's an even function. And here, instead of a plus, I'll turn that into a, like this, I times the negative of 1 over r sine theta. That wasn't really necessary to factor the negative out, but I just think it looks a little cleaner to see. I guess we'll see in a moment, won't we? So the whole point was to write this as 2 functions. Here's the function that doesn't depend on I. And then here's a function that does, so we should be able to factor the I out and get r sine minus 1 over r sine. And you can see why I wanted to factor that out, because now you can just see the dependence. Like, it only depends on cosine of theta. It doesn't also depend on cosine negative theta. So it's a little cleaner to write. Our first function is r plus 1 over r times cos. And our second function is, again, r plus 1 over r times sine. And that's it for that one. So that was 2 different ways to decompose this function, using rectangular or using polar coordinates. I think the book had wanted polar for some reason. Maybe so that you see this sort of behavior. It certainly looks a lot nicer in polar. You see this sort of z plus 1 over z is being reflected here again, and then of course the real part is cosine and the imaginary part is sine. So it has kind of an elegant way that it breaks up. All right. I'm looking at 31. We are back in a simpler class. This is a pre-calc question about lines. Find the equation of a line passing through 3, 6, and 6, 8. Well, what I immediately do, this is the form that your answer is going to take, right? I guess there are other forms you could certainly use, like this is point slope form, or I don't know, I think of this as standard form, although a lot of people will say ax plus by equals c is standard form. There's other forms that your answer could take. You could also go like y minus a point equals slope times x minus a point. So those are the 3 forms that I'm aware of that you could legitimately say this is the equation of a straight line. This is one's often called standard, I suppose, and this one's called point slope. So I usually do point slope. It's a little more useful because it's in this function format already. But if you're feeling lazy, you could certainly do this also. Nothing wrong with that. But for all of these problems, the first thing you got to do is get the slope, which is, delta y over delta. I'll go ahead and write that. Change in y over change in x. So as long as you go the same direction, we should have no problem. It's okay if they come out negative. Like you could do 6 minus 8, but if you do that, you'd better do 3 minus 6 on the bottom step, on the denominator. I'm going to go y2 minus y1, like 8 minus 6, and then downstairs we get x2 minus x1. So I'm getting 2/3 as a slope. Now that I know the slope, we could be done real quick, frankly. You could just say like x minus, pick one of these points and plug it in here, and just throw the 2/3 there, and you're done. You still have a y and an x in your answer, but I like to do it in this form. In fact, now that no, it doesn't matter. It doesn't really matter for number 2. You could do either way. So one answer, if you just wanted to grab like this point, you could say, all right, y minus the y value is our slope times x minus the x value. I should say x coordinate, That's fine. There's nothing really wrong with that. It's not in this functional format where you're able to plug in an x and see what the y is yet, because you haven't added 6. So we could actually convert this to that if you want. We would just add 6. We'd get, let me distribute this now, okay? 2/3 x, and then 2/3 of 3 is 2, so you get minus 2, and then finally I'm going to add 6. So it looks like our y-intercept, the b value, was 4, apparently. And that's the answer that I would like to give most of the time, but there was nothing really wrong with this either. Either one's fine. For part 2, though, it says find the equation of a new line, a different line. This one's going to be perpendicular to the previous. All right, if you started at, I guess this is another thing. If you want to draw it, you probably want it in this format. You're used to drawing like y equals a function of x. This format's kind of, I would have to plot maybe the 2 points and then connect the dots, and that would be a fine way to plot it, to plot this straight line. But this one, I can see 0, 4 is the y-intercept. And then a slope of 2/3, well, like a 45-degree angle would be 1, a slope of 1. 2/3 is a bit less than that, so we're going to come in like this kind of angle is fine. That's a good sketch. And the concept, of course, is that like at 3, you should get 6 for a height. And at 6, you should get 8 for a height. We want, in this new example, to construct a perpendicular line, perpendicular to this previous line, and then it passes through 6, 8. So in this image, we almost want to we want to construct this line. That's part 2, is find a line perpendicular to this guy passing through 6, 8. So all you do is, again, first target that slope. Let's call it M2 this time. And I just happen to remember that like the product of 2 slopes will be -1 if it's perpendicular. So that's something that I would suggest you memorize if you're doing these kinds of problems. Otherwise, you can't get past step 1. But yeah, the new slope will be -1 over the old. In our case, it'll be -1 over this fraction. That is -3/2. So there's our new slope. I would just write, in fact, we can do it the same way again if you wanted to get lazy. Like, just plug in the slope there, and boom. You can even use, well, I guess we're using a different point. We're using 6, 8, but I'm going to go ahead and do it my usual way. I would write like this, and then I have to go back and solve for the b. So now my second step of this question, like first step is get the slope. Second step is to rewrite what your answer would be. We have like a model for a line. Rewrite your answer using this current data that you have. The slope is -3/2, so we pop that in there. So find b. Step 2 is to rewrite this and then find b using whatever point you know is on the line. In our case, it's 6, 8. 6, 8 is supposed to be on the line. So using the fact that 6, 8 is supposed to satisfy this equation. So I'm supposed to get 8 out for y if I plug in 6 for x. And this should be enough to get us the b value. As you can see, it's the only unknown. So we have one equation with one unknown. And 6 over 2 is 3. So this is a lot like negative 3 times 3. Like if you group these as 6 over 2, right? Negative 3 times 3. So if I add 9 to both sides, that's our b value, 8 plus 9. If I add negative 3 squared, I should say if I add 3 squared, it'll cancel out and you get 9 plus 8. So final answer on part 2 is that's the slope, and then the b value would be 17. So this intersects way up at 17. If we were to draw it, 17 minus 3 halves, which is like steeper than a 45-degree angle. That's the kind of line that would hit at 6, 8 and be at a right angle when it does so. That's our pre-calc. Number 32 is a discrete question. So like right now, I taught a discrete math class, but maybe it was almost more like a finite math class. I realize what is even the difference, but what I found is discrete is an umbrella term. Discrete is a broader category. Finite math is like a subset of discrete math. Discrete math sometimes includes stuff like graph theory. Finite math will usually focus more on like even compound interest is in that class. Combinatorics stuff early on, like counting principles. So that's what this one's about. You might see voting methods. You're more typically seeing voting methods in like a discrete math class than a finite math class. But it could show up in both, I suppose. But what I've noticed, like when I taught finite math, it was also often like playing the role of just a general early course in math. So we would include polynomials, even though polynomials are effectively continuous, like they have a variable x, and that x is just a real number. But we would still talk about polynomials in a finite math class. So for this set of problems, you're eventually going to see, well, this is very discrete. And this one's pretty discrete too, but you can see what I mean. Like they're pretty computational, and they're not just logic problems. They're probably going to involve some polynomials eventually. I'm just warning you now. So yeah, the discrete question says, how many committees can you make if you're choosing from 10 people? And we have 3 different questions here. So this is one that requires you to be familiar. I guess I won't derive it right now. I just want to answer the question. But there's a formula that gives you the number of, say, objects. Say you choose R objects from a set of n. So I'm implicitly assuming here R is less than n. I'm also assuming these are positive. Well, I guess they could be 0, but it gets not very interesting if you're choosing from 0 people, right? Anyway, there's a formula for this combination. This is also the function NCR, if you've got a calculator with you or you've seen this before. N factorial over, this is a way to list just the permutations of R people. So it's like n times n minus 1 times n minus 2, all the way down to n minus r plus 1 is the last factor. And then we remove the ordering of those R objects, of those R tasks that you performed. So the way I usually compute this number is to write out, that's this left-hand part, and then I still divide by R factorial. That's the same thing. This top part is a permutation of R objects chosen from n. But we're not doing permutations. We don't care about the actual order of these people. We just care whether they're in the group or not. So for part 1, there's no restrictions. You have 10 people. Here we're doing n equals 10. Probably should have read this better, huh? Yeah, I definitely meant to include a size. I'll go edit this. It's hard for me to do this if there is no R value. So we can see that they were choosing from a group of 10, but I wonder, yeah, I meant to put a size here. Usually you'd do like, of size 5 or whatever. So if you still just want an answer for this question, that's the answer. Well, how many committees in general? I guess you would sum this as R goes from like 1 to 10. It could be a committee of all 10 people. Maybe it could be a committee of no people. But that was not the way this question was supposed to go. So let's assume it was like committees of size 6. Let's make it size 6. So select 6 people from a group of 10. From a group of 10. In that case, it would simply be this answer, and then you use a formula. And we get 10 factorial over something like this. So you could do 10 times 9 times 8. If you don't want to grab a calculator, this is what I would usually do. And then 4 times 3 times 2, some of those factors cancel, So like I can see 4 by 2 cancels with 8, 4 by 2 cancels with 8, and 3 and 9 cancel to give you 3. 3 by 7 is 21, so I'm getting a final answer of 210. If we do R equals 6. I'm going to keep going with R equals 6. Second part says, what if both Jim and Pam are on the committee? So like we have 2 people in the group that are called Jim and Pam, and we want both of them to be on the committee. Well, then you don't really have to do that task anymore. If you have 2 people in mind, like Jim and Pam are on the committee already, then you don't have to select those 2 people. Then we need only 4 more. So, and we're not choosing out of 10 anymore because Jim and Pam are in that group. So you remove them from the group of people you're selecting from. There's like a pool of 10, but 2 of them, we got a pool of 10 people, 10 objects, but 2 of them we are guaranteed to use. So we still have like 4, 1, 2, 3, So we still have like 8 others to choose from. And out of those 8, we don't need to choose 6 anymore because we already know 2 of them are taken up by these people. So we only need 4 more. So you get an answer like that. And if you're doing this by hand, you get something like 8765. You still divide by 4 factorial. Again, we can do biggest numbers. 3 over 6 is like 2. So I'm getting 10 times 7. I'm getting 70 this time. And then for the last part, one of them but not the other is on the committee. Well, okay, first of all, there's going to be 2 ways to do that. Like either you picked Pam or you picked Jim. But once you do that, we don't select Jim or Pam in the pool, so it's similar to this. But we still need, we still need 5 more people because we only put 1 of these people in there. And I'm saying 2 times because we don't know if it's Jim or Pam. So, yeah, I would do that. 8 choose 5 is a lot like 876 divided by 5 factorial. Or I guess you could keep going, or divided by 3 factorial, excuse me. So we're getting 8 by 7, which feels like 56. And we got to double it as well. I haven't doubled it yet. So the real answer is 112. 112 ways, which makes sense. The only way I can really check my work is to say, well, it's less than just this general answer of selecting any 6 people. That's okay. That's a trick that comes up now and then. That's an extra condition that happens sometimes where like, oh, I want to include this object. So it changes the number that you're selecting from as well as how many you need to select. So it changes both n and r. You just subtract however many. So if they're both on the committee, we would do n minus 2 and then r minus 2, right? But if you only want one of them, well then you're still not selecting either, but you're only reducing your selection by one person because we're still missing the other r minus 1 people. So yeah, that would be the case of one of them but not the other. And then you have to double it because you didn't decide whether like Jim or Pam. So if you had said Jim is there, and neither, like Jim is there and Pam is not, then I don't need this 2 times part. It would just get 56 ways. So 56 ways with Jim, 56 ways with Pam. And our last question of the day is a calc problem. It just says find the derivatives. So I guess I'll call this like 1, 2, and 3. 1 is, we're going to rewrite this immediately because we're going to end up using the power rule. If you had something like x to the n, its derivative is n x to the n minus 1. So part 1 we have this function, and I'll leave some space for that one. 2, 6s over s cubed. That's the same as this. And so you want to write it as a power, even if it's a negative power. Then we'll be able to, then it's in this form, and I can take a derivative with the power rule. The third one looks like you must know the product rule to handle this one. We've got 2 factors. I mean, I guess you don't have to. You don't have to know the product rule. You could, this particular case, you could expand it, right? You could distribute this stuff out. There are definitely times when you must use the product rule, but if you wanted, you could FOIL this out, and you'll get an answer. You'll be able to differentiate one term at a time. Anyway, back to it. So f prime here is going to be 1/2 t to the negative 1/2. That's half minus 1. You can also write it like this if you're fancy. So that's f prime, or df dt. The second one, this is our function g. I didn't do anything to it yet. I just rewrote it. But in that case, g prime is 6 times the derivative that you get here. And then we just use this formula again. So this is our n value. We're going to pull n down, treat it as a coefficient out front, like that. We're going to leave our variable. And then we're going to decrease the variable by 1. So if you were at negative 2 minus 1 is negative 3, I believe. And you can go ahead and just, like, hesitate to say distribute, but you can combine these. You can do 6 times 2. So my final answer is something like this. That's the derivative. That's dg ds. Or s is the variable. It's usually okay to leave it with a negative power too. So you could say negative 12 s to the negative 3, but this is also the answer you might see in the back of the book or something. And then this, I'm going to use the product rule, but you could distribute this out and get a big polynomial, a big cubic, and then just differentiate each piece. But I would usually say, like, okay, this is u and this is v, and then h prime would be this formula. Derivative of the first times the second plus the first times the derivative of the second. So it should sort of be in this form. If you don't simplify it, it'll stay in that form. The derivative of this first part is 2x minus 4. And here's the second part. We just don't touch that. We just recopy it. There's v. And then here's the first part again. But now we differentiate the second factor. So derivative of the line 3x plus 15 is just the slope 3. And we could clean that up, or we could leave it alone. We don't really have to do any further with this. Usually I would give this full credit if I was grading this, you know. But if you're just bored and you want to do this out, 15 times 2 feels like 30. 15 times 4 feels like 60. And then we're over here, and we get 3x squared minus 12x. So I'm getting 9x squared I mean, I don't know why I'm doing this, because the original function was not in some clean form, but what was the original function? 3x cubed minus 12x squared plus 15x squared minus 60x. So that's 3x squared in the middle, right? That's the original function. And our derivative, 6 plus 3 is 9. The x's have got negative 24 plus 30, so we're getting 6x, and then we get minus 60. And I'm claiming that this is the derivative of this stuff. Yep, 9x squared plus 6x minus 60, so that checks out. I'm going to disappear, folks. That was another set of solutions to our Math Challenges website. Current problem was this calculus one, but I post new problems every weekday. So this one will be up for the weekend. And on Monday, as you can probably predict, we will start a Calc 2 problem. So Calc 2 through abstract algebra for next week. All right, folks, thank you for tuning in. Have a magnificent day.